All right, 6.4, we're now going to talk about shapes of these molecules. Now that we know how to draw the Lewis structures, once you draw them, you can put them in different shapes, okay? And these are basically the different types of shapes. This section is not hard. It's just there's a lot of vocabulary words that you kind of have to know, um, and you have to kind of pay attention to them. I'm going to kind of show you a chart that has all the names, and this is something that I will give to you on the exams. You don't have to necessarily memorize the names, you just have to kind of understand how they apply. So I care more about the understanding than you just trying to hardcore memorize all these names, okay? And shapes come from this theory called what's called valence shell electron pair repulsion, or the VSEPR model. And basically what it is electrons, groups of electrons, or electron groups. We're going to use this term a lot, electron groups, or groups of electrons. Want to be as far away from each other as possible, okay? So imagine I have a central atom, okay, and I've got other atoms around it. I have two other atoms around it, okay? There's lots of different geometries I can draw. I can draw like this. I can draw maybe like a 90-degree angle. I can draw, I don't know, whatever. Let's do like an angle like that, okay? But let's say I have two electron groups, okay? Well, the VSEPR theory says you have two groups. There's negative charges around here and negative charges around here. All right. These two groups want to be as far away from each other as possible because of repulsion. All right, like charge repulsion. So which of these geometries would be the best case if I have two different groups? Well, this one would be. All right, 180 degrees. These two electron groups, this is the furthest possible bond angle that we can get so that these groups are as far away from each other as possible. Okay, let's say you had three groups around it. What would be the bond angle? Okay, well, obviously we would not want something like this because these groups are very close to each other. Okay, so what bond angle, what kind of geometry would it be if you have three groups as far away from each other as possible? And this is what it would look like. Okay, it would be this kind of a geometry. Okay, so you can kind of see, here's one that I already talked about. That last one I just talked about is this one, trigonoplanar. All right, what happens if I have four groups? Well, it's something called a tetrahedral structure. This is kind of more of a three-dimensional where you have, it's kind of like a tripod. So imagine a tripod for like a camera or something like that. These four groups, I'm trying to do with 3 dimensions, are in a tetrahedral form. Here's kind of the form of that right here. So like this bond right here is coming out towards you. Okay, so these three groups are our main geometries. It's what's called electron group geometries. These ones here are a different type of geometry, but we'll talk about them. Okay, and that's basically what VSEPR theory is. You want these things as far away from each other as possible. Okay, so this is kind of where it starts. The book, now I'll probably do more of this inside class as a lecture, but this is kind of a good start so that you can understand it, okay? So let's just talk about the number of groups, or what's called electron groups. Let me first explain what electron groups are, and then we'll go back to that previous slide, okay? Electron groups are any group that contains an atom or a lone pair. It's any group that's basically an atom or a lone pair. So like if I have, let's say, water, for an example. Let's take water. Water has a lone pair, and has two atoms. If I'm just looking at the oxygen atom, just pay attention to oxygen. And I'm going to look at the number of electron groups, around oxygen. Now, this is a very simple concept. People tend to make it harder than it really is, okay? The number of electron groups around oxygen, okay? So I'm going to count the total number of atoms and lone pairs, okay? Well, this oxygen has one lone pair, and it has a second lone pair. So it has two lone pairs, and it has this hydrogen atom and this hydrogen atom, and it has two atoms. So the total number of electron groups is 4. All All right, so oxygen has 4 electron groups around it. Let's say we took CO2 as an example. Okay, this is the structure of CO2. All right, I'm looking at the central atom only, carbon. Carbon has, let's put atoms plus lone pairs. It's got this oxygen and this oxygen, so 2 atoms, and it's got 0 lone pairs. So CO2 has 2 electron groups around it. All right, and this is all it is. All right, if we were to take, I don't know, let's say like this compound, just to kind of give you some more examples. All right, so I'm looking at the central atom, looking at the sulfur. I'm not looking at number of bonds, I'm just looking at the number of atoms. So atoms plus lone pairs. So this sulfur has 1 lone pair attached to it, and it's got this oxygen and this oxygen, 2 atoms. So it's got 3 electron groups. That is all you need to do. That's all you need to determine an electron group. Electron group is either an atom or a lone pair. You basically add up the total, and that's how many total electron groups you have around it. So if we go back to this example, all right, I'm going to kind of draw a line here. This is kind of showing you examples of things with 4 electron groups. You can either have 4 atoms attached to it, like CH4. CH4 looks like this. Okay, notice you have 0 lone pairs, so it's 4 atoms and 0 lone pairs for a total of 4 groups. All right, if we look at the next one, we have 3 atoms and 1 lone pair. See the lone pair right there? And then we obviously have atoms attached here. All right, it's forming bonds like NH3. This is the structure of NH3. Okay, it still has 4 electron groups around it. All right. And then here's water, an example. You have 2 atoms plus 2 lone pairs for a total of 4 groups. So all of these have 4 electron groups. Their geometries are going to be a little different of a name when it comes to this, and we'll talk about this when we get to that slide. I'm just trying to show you all the possible examples. All right, here's a case where you have 3 different atoms around it. All right, so for example, in the CO3 case, you have oxygen, oxygen, a carbon, and an oxygen. So 3 atoms plus 0 lone pairs, 2 atoms plus 1 lone pair, or just 3 atoms as well plus 0 lone pairs. Okay, all right, so these all have 3 electron groups. You can also have an example where you have 1 atom plus 2 lone pairs, which would be like an oxygen, like this is an example of one. Okay, it doesn't really matter what's attached. Let's just put hydrogens here. So now it really wouldn't be a central atom. I think they're just really implying central atoms. This oxygen is not a central atom, but technically this is a case where we have 1 atom, which is our carbon, plus 2 lone pairs. Okay, and then you can have 2 groups, like the CO2. You have 2 atoms here. All right, again, you have an atom here. This would be a nitrogen or a hydrogen. This would be a Cl or a Cl. All right, where again you can have atoms or lone pairs or whatever. Okay, so here they kind of actually show you balloons to actually show you the actual structures, which I think is kind of cool. So this one is kind of the tetrahedral shape to it. Tetrahedral. These are the names you kind of have to get rid of, learn. This is trigonal planar. All right, and this is linear. Okay, and it's basically just showing you that the balloons want to be as far away from each other as possible. Okay, so molecular shapes, here's just an example of a tetrahedral, CH4, we have 4 electron groups around it. Again, you want things to be as far away from each other as possible. Here's another example where you also have 4 groups, you still have 4 electron groups, but one of them is a lone pair. Okay, and then here water, you still have 4 electron groups, but 2 of them are lone pairs. Okay, so let's talk about these names. The names, there are 2 different names. There's electron group geometries. Again, this is not hard. There's just a lot of different names that you have to know. All right, there's electron group geometry, and then there's molecular shape or a molecular geometry. Okay, so, and basically I'm going to give you a list that looks like this. Okay, if you have four groups around your molecule, it doesn't matter if it's atoms or atoms and lone pairs or just lone pairs. The electron group geometry is always tetrahedral. 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 Tetrahedral is the name for the electron group if you have four groups around it. Now, if you change the number of lone pairs, you actually change the name or the number of atoms. So 0 lone pairs or 4 atoms, okay, is called tetrahedral molecular geometry. If you have 1 lone pair and 3 atoms, it's called trigonal pyramidal. Because if you notice, if you ignore the lone pair and just look at the shape of your atoms, notice it's like in a pyramid shape. All right, so it's kind of a pyramid. I think that my drawing actually made it look worse, but basically it's in a pyramidal shape. So you call it trigonal pyramidal. That's the molecular shape. All right, the electron group geometry is still tetrahedral because you still have 4 groups around it. But if you just ignore the lone pair and just look at the atoms, the shape of the atoms, it's in a pyramid shape. All right, if you have 2 lone pairs and 2 atoms, then it's called a bent structure because it actually looks like this. All right, if you notice, every time I draw water, I draw it like this, the lone pairs here, because I'm trying to show you a bent geometry. So this is actually a bent geometry. They're actually showing it to you at an angle. Okay, so all tetrahedrals have 4 groups around it, and they could be any combination. 0 lone pairs and 4 atoms, 1 lone pair and 3 atoms, or 2 lone pairs and 2 atoms, but they have different molecular shape names. Okay, and you kind of have to know these. All right, but like I said, I'm going to give you a chart that looks like this on the exam. Okay, now let's do the same analysis for 3 groups. What happens if we have 3 groups? Well, trigonal planar. Okay, all electron groups are trigonal planar. Notice trigonal planar, trigonal planar. All right, if you have 0 lone pairs and 3 atoms, it's called trigonal planar. So notice these names are the same if you have 0 lone pairs. If you have 1 lone pair and 2 atoms, all right, it is called, this is incorrect, it is not called trigonal planar. This is an incorrect name. This should be bent. All right, so ignore this off the slide. Okay, trigonal planar with 0 lone pairs is called trigonal planar. If you just have two atoms, so 1 lone pair and 2 atoms, it's called bent. You have a bent geometry. All right, and then linear is pretty easier. It's linear. It doesn't matter if you have lone pairs or atoms or whatever. Like if you have 1 lone pair, 1 atom, like in a cyanide like this. All right, notice this carbon still has 2 groups. You have a lone pair here and an atom here, but notice it's still a linear geometry. Okay, so like I said, I'll probably go over this again in class just to make sure you understand it, but that's basically how you determine the shapes. Also, notice the bond angles. Linear is 180. Tetrahedrals are always 120, and then tetrahedrals are 109.5. Okay, so hopefully this makes sense. Let me see what this slide is. When the central atom is surrounded by 2, yeah, so I just talked about that, 2 electron groups. Oh, here are the bond angles again. I just talked about this. 180 for linear, 120 for trigonal planar. Now remember, trigonal planar can have either trigonal planar or bent geometry in the molecular geometry. All right, and then tetrahedral, you can have, remember, tetrahedral, or you can have pyramidal, trigonal pyramidal. You can either use pyramidal or trigonal pyramidal. I think that's OL, or bent. Okay. Nothing new here. We already talked about this. Molecular shape. With practice, determining the shape of a molecule or polyatomic ion is a relatively easy process. However, it's very important to follow the procedure. Okay, so like if I give you a molecule, let's say like NO3 minus, and I ask you what is the geometry of this molecule. Well, the first thing you have to do is draw a Lewis structure. Then you got to count how many groups are around it, and then you have to figure out, based off of the chart, what you have. All right, so NO3, first doing the Lewis structure, the valence electrons, the skeletal structure, coordinate covalent bonds, and the remaining, yada, yada, yada. We're not going to go into it, but that's the structure of NO3. All right, so what is the electron group geometry? It is trigonal planar. What is the molecular shape? Well, 3 atoms, 0 lone pairs. It's still trigonal planar. All right. Is there resonance? Yes. I threw that in for good measure. So number 5, let's put number 5, resonance. We'll put it as a question mark. Yes. How do I know? Because I have a double bond here. Okay, so that's basically what the 6.4 is. It's determining, it's basically applying everything that we learned in this chapter all in one. Okay? So here's some practice problems. Hey, look at that, NO3 minus. We just did that one. All right, why don't you do NCl3, and when you come back, we can go over that one. All right, welcome back. If you did the Lewis structure, you should get this for the Lewis structure. So how many groups are around my nitrogen? There are 4 groups. Therefore, the electron group geometry should be tetrahedral. But what's the molecular geometry? You should say pyramidal. Okay. So, and the bond angles, these are 109.5, these are 120 because it's trigonal planar. Okay. So here, trigonal pyramidal, but you also still have tetrahedral that goes with it. Okay, so I will see you when you come back for 6.5, electronegativity and polarity. Oops, sorry about that.